Hello students, welcome to AIMS online classes. This is a chemistry session. Here we are discussing about classification of elements. See, in the earlier classes we have seen how different scientists they have tried to classify elements on different bases, about modern periodic table and different namings of the elements in the modern periodic table, like general characteristics or features of modern periodic table we have seen. In this session, we are going to see about periodic properties of the elements, periodic properties of the elements and how they are being trend in a group and period, how they are varying in the groups and periods we are going to see here. Okay, let us see in this session especially about valency and atomic radius we are going to see. The modern periodic table, as we know, it is organized on the basis of electronic configuration of the elements of the atoms of the elements, isn't it? Yes, this modern periodic table is organized or constructed based upon the atomic number as well as the electronic configuration of the atoms of elements. So, physical and chemical properties of the elements are related to their electron configuration, particularly the outer shell electron configurations. Yes, the properties of the elements, like physical and chemical properties of the elements, are mostly related to their electronic configurations, particularly to say their valence electronic configuration or outer shell electronic configurations. The atoms of the elements in a group possess similar electronic configurations, isn't it? We have seen in a group all the elements will possess same kind of valence electronic configuration. That is to say, general electron configuration of elements in a group will be same. Of course, only one exception is there, that is noble gases with helium. But remaining all groups, if we observe, all the elements in a group possess similar valence electron configuration. Therefore, we expect all the elements in a group should have similar chemical properties and there should be a regular gradation in their physical properties from top to bottom. So they should show similar chemical properties. There should be some gradation, either increasing or decreasing of physical properties from top to bottom. Okay. Similarly, across a period or across a period in the modern periodic table, that is from left to right, in any period, elements get an increase in the atomic number by 1 unit between any two successive elements because atomic number increases from left to right in a period. So one electron is being increased, isn't it, from element to element. Therefore, the electronic configuration of valence shell of any two elements in a given period is not same. Why? Because in a period from left to right, from element to element, atomic number is being gradually increasing. As atomic number increases, number of electrons gradually increases from element to element as we move from left to right in a period. So this concludes that the electronic configurations of valence shell of any two elements in a given period are not same. Due to this reason, elements along a period possess different chemical properties with a regular gradation in their physical properties from left to right. So as there are no elements with the similar electronic configurations in a period, there will be no similar properties for any elements. So there will be regular gradation from left to right among these physical properties of the elements. To understand this, how these properties are being related from element to element in a group on period, let us take some properties of the elements and let us discuss how they vary in the groups and periods. Okay, first let us see here the properties of the elements and their trends in groups and periods. How do they vary in the groups and periods? We are going to see here. First among them, let us see here about valency or valence. So valence or valency of an element was defined as the combining power of an element with respect to hydrogen or oxygen or indirectly any other element through hydrogen and oxygen. Okay, valence is defined as the combining power of an element or the combining capacity of an element with respect to hydrogen or oxygen. If you say in terms of hydrogen, valence of an element with respect to hydrogen is defined as the number of hydrogen atoms with which one atom of that element chemically combines is known as its valency. Means how many hydrogen atoms are combining with one atom of an element is considered as its valency. That is definition in terms of hydrogen for valency. Generally to say, it is defined as the combining capacity of an element. Combining capacity in terms of hydrogen, if you take with how many number of hydrogen atom one atom of an element is combining is taken as its valency. For example, let us see here one example. One atom of sodium chemically combines with one atom of hydrogen to give sodium hydroxide. NaH. It is called sodium hydride. Sorry, sodium hydride. So in this, if you observe, one atom of sodium combined with one atom of hydrogen. What we defined here valency, the number of hydrogen atoms combining with one atom of an element is called its valency. So here one atom of sodium combining with one atom of hydrogen. Now we can say therefore the valency of hydrogen as 1. Okay, if you see one more element, we know magnesium. Magnesium combines with hydrogen to give magnesium hydride. The formula of magnesium hydride is MgH2. Here, magnesium combined with two atoms of hydrogen. One atom of magnesium combined with two atoms of hydrogen. That's why the valency or the combining power of magnesium in terms of hydrogen is considered as 2. Nothing but the valency of magnesium is 2. Okay. Another way, the valency of an element with respect to oxygen is defined as the twice the number of oxygen atoms with which one atom of an element that combines. Okay, the twice the number of oxygen atoms which are combining with one atom of an element is considered as its valency. Let us see this also with one example. For example, one atom of calcium combines with one atom of oxygen to give calcium oxide, CaO. So here, one atom of calcium combined with how many oxygen atoms? One oxygen atom. So in terms of oxygen, valency is defined as twice the number of oxygen atoms that combining with one atom of an element. So here, one atom of calcium combining with one oxygen atom. So if you make it twice, 1 into 2, that is 2. So the valency of calcium is 2 with respect to oxygen. Okay. So this the group number of an element gives the maximum valency of that element as per old notation, that is Roman numbers 1 to 8 groups. For generally elements of 1 to 4 groups, directly the group number is considered as maximum valency. If we say first group elements, 1A group elements, so their group number is 1, so their valency is considered as 1. If we see third group elements, their group number is 3, so their valence is considered as 3. And for the higher groups, more than fourth group, that is the fifth, sixth, seventh groups, for them it is considered another way that we are going to see here. In general, the valence of an element with respect to hydrogen is traditional group number. If the element is in the group 5 or above, its valence is 8 minus group number. Okay, if the group number is in between 1 to 4, directly the group number is considered as its valency. Suppose first group elements, 1A group elements, all kilometers we say them. For them, the valency is directly which is equal to their group number, that is 1. If you see third group elements, boron family, for them group number is 3 and the valency for those elements also is considered as 3. If the group number is greater than 4, that means groups from 5th, 6th, 7th and 8th groups. For these group elements, valency is considered as 8 minus group number. For example, 7th group elements are the chlorine. One of the 7th group elements is chlorine is considered here. The valency of this chlorine is considered as 8 minus its group number. We know chlorine belongs to 7th group, isn't it? So for 7th group elements, valency is considered observed by taking the formula 8 minus its group number. So 8 minus group number of chlorine is 7. So we get it as 1. So the valency of chlorine is 1. In this way, for the group elements in the groups 1 to 4, directly their group number is considered as their maximum valency. And for the elements in the higher groups from 5th to 8th group, for them valency is considered by taking the formula 8 minus their group number. Okay. In general, each period starts with valency 1 because each period starts with alkali metals for whom the valency is 1 for first group elements, and it increases up to 4 with respect to the group number, and then again it decreases from 4, 3, 2 to till 0 in the following groups. Okay, this is applicable only for the main groups generally, that is S block and P block elements. A subgroup yes. Okay, see here the valencies of first 20 elements are mentioned here. If you see in a period from 1 to 0 it is taken, and we know these elements are in the second period, isn't it? From lithium to neon. What happened for the valencies of these elements? If we observe from 1, it is started with 1 alkali metal and it increased till 4 and again it decreased till 0. And if you see next period again, third period it is. If you observe for these elements, it is started with 1 valency, first element in this period. Gradually it increased till 4. Again it decreased till 0. So in this way, in a period, valency it starts with 1 for the starting element, gradually it increases till 4 and then it decreases gradually till 0. Okay. Next property, atomic radius. Atomic radius of an element is defined as the distance from the center of the nucleus of the atom to the outermost shell. If you consider this as a hydrogen atom, for this, from the center, from the nucleus to the outermost orb of this hydrogen atom is considered as radius or atomic radius of hydrogen. The distance between the nucleus and outermost shell of an atom is considered as atomic radius. Atomic radius of an element is not possible to measure in its isolated state. We are telling just as definition the distance between the nucleus and the outermost orbit of an atom as atomic radius. But in fact, atomic radius of an element is not possible to measure in its isolated state because it is not possible to determine the location of an electron that surrounds the nucleus. Yes, we cannot locate the exact position of the electron in its orbit. So we cannot identify where the orbit is exactly because there is no construction. Just the path where electron is revolving around the nucleus we are considering as orbit. As we are not able to locate the electron exactly, we cannot say where the outermost orbit of an atom exactly. So we cannot calculate or estimate the atomic radius of an isolated atom, as we cannot estimate the where the outermost orbit exactly. Okay. However, we can measure the distance between the nuclei of adjacent atoms in a solid. Yes, we can estimate the distance between the two nuclei of the adjacent atoms in a bonded molecule. From this, we can estimate the size of the atom by assigning half of the distance to the radius of each atom. So, the distance between the two nuclei of two bonded atoms can be measured like this. Suppose this is a distance between the two nuclei of two bonded atoms. If it is measured, the half of this is taken as a atomic radius of that atom. Okay, from the isolated atom, atomic radius cannot be calculated because we cannot estimate where the outermost orbit is. As electrons are revolving with very high velocity, we cannot locate them, and hence we cannot identify where the outermost orbit is exactly. So we cannot say the atomic radius for individual atoms, but we can calculate the distance between the two nuclei of a bonded molecule. So if you're able to calculate that, then the half of the distance is considered as a radius of those atoms. Okay, this method is best suited to the elements such as metals that exist in the solid state. More than 75% of the elements are metals, and atomic radii of metals are considered as metallic radii. Okay. Another way of estimating the size of the atom is to measure the distance between the two atoms in a covalently bonded molecule. Not only metallic radii, even covalent radii also can be considered because most of the molecule there will be the covalent bonds. So in the other way, we can estimate the size of the atoms by measuring the distance between the two atoms in a covalent molecules. Then that radius observed is called covalent radius. The size of, for example, the size of chlorine atom is estimated by measuring the length of the covalent bond between two chlorine atoms in a chlorine molecule. Suppose two chlorine atoms combine together to form a chlorine molecule through covalent bond formation. Now, if the distance between these two chlorine atoms in this chlorine molecule, if it is measured, the half of this distance, is taken as atomic radius, which is called as a covalent radius of chlorine atom. Okay, here two chlorine atoms are bonded together with covalent bond. Now we call this chlorine molecule. If it is calculated the distance between the two nuclei of these chlorine atoms, that is called bond distance. Now half of this, for example, if it is, see here the measurements also mentioned, the chlorine bond distance is 198 picometers. 198 picometers. The half of this is 99 picometers. The half distance. This is considered as atomic radius or covalent radius of chlorine atom. Okay. Generally, atomic radius is measured in terms of picometers and angstrom units. Picometers, angst, because the atomic radius is defined as the distance between the nucleus and the outermost orbit. As it is a distance, it can be measured with the units of distance like meters, centimeters, kilometers, millimeters, centimeters. These all can be used. But these atomic radii are as micro quantities. Generally, they are measured in picometers or angstroms. We know here 1 picometer is equal to 10 to the power of minus 12 meters, which is also equal to 10 to the power of minus 10 centimeters. And we told here one more unit for the atomic radius is angstrom units. We know 1 angstrom is equal to 10 to the power of minus 10 meters or 10 to the power of minus 8 centimeters. They are generally used units for the atomic radius. In calculation, in the problems, in the calculations, they may give some other units also. So by using these unit conversions, we can convert into the desired quantities. Okay, next, variation of this atomic radius or atomic radii in a group. How this atomic radius varies in the groups. Atomic radii increase from top to bottom in a group of the periodic table. That means in a column from top to bottom, atomic radius increases. Why? Because as we go down in a group, the atomic number of the elements increases. Therefore, to accommodate the more number of electrons, more shells are required. So as a result, the number of shells in a group from top to bottom increases. We see in a group from top to bottom, from element to element, a new additional cell will be existing. Number of shells increases from top to bottom to accommodate more number of electrons. And hence, the distance between the nucleus and outermost shell of the atom increases. Yes, as number of shells increasing, the distance between the nucleus and outermost shell increases. So we can say, hence, the atomic size increases from top to bottom in a group with atomic number increases. Okay. Why it is increasing in a group from top to bottom? Because number of shells increases from element to element as we move down in the group. So the distance between the nucleus and the outermost shell increases, hence the atomic radius is said to be increased in a group from top to bottom. See here, suppose if you consider these groups, if you see the first group, what is happening here? The number of shells, let us observe. We know hydrogen configuration as 1s1 means it has only one shell, isn't it? If we see next element in the same group, lithium, its configuration is 1s2 2s1 means there are two shells in its configuration. What happened here? From hydrogen to lithium, one shell is increased. If we see next element sodium, it has three shells. So what happens to the size then? As number of shells increasing, size increases, and hence distance from the nucleus to the outermost orbit also increases. If we see for potassium, there will be four shells. So there will be four shells. And for rubidium, there are five shells. And for cesium, there are six shells. And for francium, there are seven shells. So in this way, as you move down in a group from top to bottom, number of shells increases from one element to element, and hence the distance between the nucleus and the outermost orbit increases. Thereby, we can say atomic radius in a group from top to bottom increases. The same concept you can apply for all the groups in the modern periodic table. In a group, any group, in a group from top to bottom, atomic size or atomic radius increases. Okay, now let us see how does this atomic radius vary in the period. That is variation of atomic radii in a period. Atomic radii of elements decreases across a period from left to right. Why? Because as we go right, electrons enters into the same main shell in any period. Isn't it? If you observe in any period, number of shells won't increase even if move from left to right. Number of shells are maintained the same for all the elements. So for all the elements, the last electron enters into the same shell. Even for inner shell, for some elements, the last electron enters into inner shell in case of D and block elements. For S and P block elements, electrons enters into the same shell for all the elements. But for D block and F block elements, even the last electron enters into last but one shell, that is penultimate shell, D subshell, isn't it? Therefore, there should be no change in the distance between the nucleus and the outermost shell. So all the elements should have almost same size because last electron is being entered into almost all the elements for in the same shell. So there should not be any change in the shell size. But nuclear charge increases because of the increase in the atomic number of the elements in a period. But what happens in a period from left to right, atomic number increasing. Because of the increase in the atomic number, nuclear charge increases, that is positive charge increases from element to element. At the same time, number of electrons in the last shell also increasing. Because of the increase in these two, nuclear attraction on the outer shell electrons increases. As a result, size of the atoms decreases. That is why we say from left to right in a period, atomic size decreases. Did you understand the reason why the atomic size decreases in a period? Because as we move from left to right in a period, the nuclear charge increasing element to element. At the same time, number of electrons in the outer shell also increasing. As these two are increasing, between these two, that means between the nucleus on the outer electrons, attraction also increases. What happens? Attraction increasing, they come close to the nucleus. Hence, size decreases. So we can summarize as atomic size decreases in a period from left to right. See, one example it is mentioned here. These are second period elements, isn't it? From lithium to fluorine and neon also will be at last. So till halogens it is shown here. From lithium to fluorine, if you observe, for these all elements, last electron is present in the second shell only. See here, for lithium there are two shells, for beryllium also two shells, even for fluorine also two shells only. But if you observe carefully, for lithium there is only one electron in the outermost shell. For beryllium, two electrons in the outermost shell. In this way, as we move from left to right, number of electrons in the outermost shell increasing. If you see for fluorine, there are 7 electrons in the outermost shell. Number of electrons in the outermost shell increasing as we move from left to right. Along with that, nuclear charge also increases. If we see lithium, it has 3 units positive charge. For beryllium, 4 units. If we see for fluorine, 9 units. Means nuclear charge increased and the number of electrons in the outermost shell also increased. Between these two, attraction increases. So these electrons will come a little close to the nucleus from all the sides and hence size decreases. That is why we say in a period from left to right, atomic size decreases. Okay, this we see here. This is a summarization of atomic radius in the groups and periods. What we can say? In a group, from top to bottom, atomic size increases as number of shells increasing from one element to another element. And what about in a period? In a period, atomic size decreases from left to right as nuclear charge and outer electron cloud increasing. Between these two, attraction increases and hence size decreases. Okay, this is about a variation of atomic radius in the groups and periods. In groups it increases, in periods it decreases. Now let us see comparison of size of the atoms with the anions and cation size. That is comparison of size of the anion or cation with the parent atom, that is neutral atom. The size of the anion will be greater than that of its parent atom. The size of the cation will be smaller than that of its parent atom. So before going to understand this, let us know first about this anion and cation. What is anion? What is cation? We know anion means the charged particle formed by the gain of one electron by the atom, one or more electrons. When an element or atom gains one or more electrons, then it forms a negative ion which is called as anion. Then what about cation? In the reverse way, the ion formed by the atoms by the loss of one or more electrons is called cation, that is positive ion. So anions are negative ions, cations are positive ions. These are formed by the gain of electrons and these are formed by the loss of electrons. Now the anion which is formed by the gain of extra electrons, for this size will be greater than that of the neutral atom because it is gaining extra electrons and hence for the accommodation of these electrons it should increase its size. That's why anions will be having greater size than that of their neutral or parent atoms. What about cations? Cations are formed by the loss of electrons. So as the loss electrons, size will be decreased because less number of electrons are there. So nuclear force of attraction will be more on those and hence size decreases. So cations are having smaller size than that of their neutral atoms or parent atoms. For example, if we see size of F minus, that is fluoride ion, is greater than that of fluorine atom because the fluoride ion is having one electron extra. So to accommodate this electron, its size should be a little increased. One more example, if you say sodium ion, the size of Na plus ion is smaller than that of sodium atom. So cations are always smaller than neutral atom and anions are always larger than neutral atoms. See here, this is sodium atom. By the loss of an electron, it has become positive ion, isn't it? So see here, suppose if it is sodium, what it is, no, not sodium exactly, they have given some other element. Anyhow, if you observe the configuration, it is neutral atom. When it lost one electron, it formed here positive ion. By the loss of an electron, what happening? Nuclear charges remained the same, but number of electrons in the outermost shell decreased. So nuclear force of attraction on these electrons increases, and hence they come a little close to the nucleus. That's why size decreases. So it is called now cation. So cation size is always smaller than the neutral atom. If you see in case of anion, it is neutral atom, and by the gain of an electron it forms negative ion, which is called anion. Now between the already existing electrons and incoming electron a little repulsion occurs, and to accommodate these all electrons size will be a little increased, because nuclear charge is being same but number of electrons is increased. So nuclear charge is being dominated by repulsive forces between the electrons, so they move a little away from the nucleus, hence size increases. So we say anion size is greater than that of neutral atom, whereas cation size is smaller than that of neutral atom. Okay, that's about anions and cation size when compared to parent atom or neutral atoms. Okay, thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates on recorded videos.